Hello there. This is a video session on what is gray code. Gray code is a code named after the American physicist and researcher Frank Gray, who worked at the Bell Laboratories. This is a non-weighted code. That means the position of the bits do not carry any weight. So for example, we are familiar with, let us say, the binary number. Let us take a binary number, say 1, 1, 0. Now we know that in this binary number, every bit has an associated weight. So if we start with the least significant bit, this has a weight of 1, this has a weight of 2, and the next bit has a weight of 4. So as far as the binary number is concerned, we say it is a weighted code. But a gray code is a non-weighted code. That means the position of the bit does not carry any weight. This is one of the most important properties of the gray code. That means the successive code words or the successive codes differ in only one bit. We will see how this becomes very useful. This is also called as a minimum change code or the unit distance code or a minimum error code. So it is also called as a minimum change code because as we go from one code word to the next, there's a change of only one bit. It is also called a cyclic code because the words are differing by one bit position only. As we go from one word to the next, there's a difference of only one bit. This code is a self-reflecting code. This is again an important property which we will see how it works out, how we can use it to generate the complete gray code. Where will this code be used? This code is useful in A to D converters or analog to digital converters, and it is also used for error detection and correction in transmission of digital signals. And of course, we'll be studying Karnaugh maps in one of the sections, and at that time we will see that gray code is extremely useful. And since there's a change of only one bit, the switching operations are reduced and it becomes a power efficient code. And last but not least, this is a very important property. This code is not suitable. It is not suitable for arithmetic operations. Right? Okay. Now let us take up these properties one by one and see how they apply to this particular gray code. Here we have the decimal numbers from 0, 1, 2, 3 up to 15. We have their equivalent binary values in 4-bit 0, 0, 0, 0, and coming to 15 we have 1, 1, 1, 1. Now the gray code is shown here. We will see how to generate this gray code, but let us study a few properties of this gray code and compare it with the binary code. First, we saw that gray code is a non-weighted code. That means the position of the bits do not carry any significance or any weight. There is a difference of one bit in successive codes, or it's a minimum change code. Now let us understand what this particular point means, and to understand this we'll use the example from this table. The decimal value of 3 is 0011. As we go from decimal 3 to decimal 4, the binary value of 4 is 0100. Now you can observe as we go from 3 to 4 equivalent decimal values, there is a change of 3 bits. For example, the bit 1 has changed to a 0. This next bit 1 has also changed to a 0, and this 0 has changed into a 1. So as we just move from one decimal digit to the very next decimal digit, the 3 bits of the binary number out of the 4, 3 bits have been modified. But let us compare that with what happens in the case of a gray code. So for decimal 3, the equivalent gray code is 0010, and for 4 the decimal code is the equivalent gray code is 0110. And you can observe as we go from 3 to 4, the gray code, the 0 bit remains the same, the 1 bit remains the same. This 0 bit has changed to a 1, but the next 0 bit remains the same. So if you compare these two gray codes which are of successive values, then there is a change of only 1 bit, and therefore we say it's a minimum change code. But here, when you compare it for binary, the change in bits was as much as 3 bits changing at the same time. But let us observe that self-reflection feature here. Let us consider the first gray code 0000 and the last gray code which is for decimal number 15. Observe that the last 3 digits of this are 000, the last 3 digits of this are 000, and the difference in their two codes is only in the most significant bit. Here the most significant bit is a 0, and for this the most significant bit is 1. Look at the next one. The next gray code is 0001, and if you compare it to this, it is 1001. Again, observe these 3 bits and the last 3 bits here, they are the same, and all that is changing is the most significant bit has changed from 0 to 1. Let us take the next one, 0011, and the third number from the bottom, it has the gray code 1011. Again, you can see that 3 bits here and the 3 bits in this, they are the same, and only the most significant bit has changed from a 0 to a 1. And this pattern, in fact, you can observe it as we go to the next pair of bits or the next one, and observe it here. Again, in this case, the last 3 bits 101, the last 3 bits 101, and where do the bit patterns differ? Only in the most significant bit. A 0 has changed to 1, and we can observe that here. So this becomes a self-reflecting code. Now, supposing we have a gray code representation of n bits. This n may be, for example, 4 bits. To obtain the gray code representation for a larger number of bits, say n plus 1 bits, we will write down the two n-bit representations one below the other. We'll see this in the example, and we will append a 0 at the beginning of every code in the first group, and we'll append a 1 at the beginning of every code in the second group, right? And the least significant bits we'll have here. Now let us start this example. In this, we have a 3-bit code that is being generated in the last column. But let us start from the beginning. We start with the 2 bits 0 and 1. These 2 bits, we can see they differ in only 1 bit, and therefore we can say this is the simplest gray code that we can generate, which is out of 1 bit. Now, how do I extend this to a 2-bit gray code? So what we'll do is we'll first take the original bit 0 and 1. These are our original bits 0 and 1. We'll create a mirror image of this pattern, so 0 and 1. So you can imagine that there is a mirror here, and we have now generated the mirror image 1 and 0. So this one, its mirror image is 1 here. This 0, its mirror image is 0. Now what we do is we take these 4-bit patterns. So we have 0 1 1 0. This is 0 1 1 0. In front of the pattern which was in front of the mirror, so we have 0 1, we'll append a 0. So 0 0. So this 0 0 gets appended to the part which is in front of the mirror as if, and coming to the part which is the reflection, the mirror reflection or the mirror image, the 1 and the 0, these are the ones and the zeros that we got, we append this with 1 1, and therefore our gray code becomes 0 0 0 1. You can see there's a difference of only one bit is changing. As we move from here to the next, 0 1 1 1, again this one bit remains the same, but the 0 has changed to a 1. Again 1 1 1 0, we can observe the 1 has changed to a 0, but this one bit remains the same. Now we create a mirror image of this so that we can have a 3-bit gray code. So how do we do that? We take these 4 bits and we write these 4 bits here: 0 0 0 1 1 1 and 1 0. Again we create a mirror image of this, so 1 0, this 1 1 becomes a mirror image here, 0 1 becomes a mirror image here, and the 0 0 becomes the mirror image. Again the part which is ahead of the mirror, or the part which is in front of the mirror, we append a 0 before that. So again let us visualize, here is the mirror, we append a 0 in front, so this become our bit patterns for the gray code. And the part which is let us say the reflection or the mirror image, we put a 1, and that becomes our gray code in 3 bits. This video is dealing with the topic of binary code to gray code conversion. A binary number can be converted into a gray code by 2 different methods. We look at both the methods in this video. The bits of a binary number, we can represent them as a set B0, B1, B2, B3 as we move from the least significant bit to the most significant bit. And equivalently, the bits of a gray code can be represented with G0, G1, G2 and G3. This is of course for a 4-bit binary number or a 4-bit gray code. Now, how do we generate the gray code values given a particular binary number? The logic will be like this. For any given n-bit number where I is 0 1 2 3, we say that G of I is the XOR of the ith bit and the I plus 1th bit. So for example, we'll have G of 0, in this case I becomes 0, G of 0 will be B0 plus B1. So the G0 here and B0 correspond to the least significant bits of the gray code and the binary code. G1 will be B1 XOR with B2. G2 is B2 XOR with the next higher bit, which is B3, and G3 is B3 XOR with B4. This is of course assuming that we are considering a 4-bit binary number, and as the bits would be increasing, the gray code also would expand accordingly. Now let us take the first method of how to convert a given binary number into its equivalent gray code. We are given here the binary number, and that is 0 1 0 1, and that is 0 1 1 0. Now before we start this, let us show our truth table. This is our XOR truth table, and as we can see in the XOR truth table, when both the inputs are identical, A0 B0, the output is 0, or when A1 B1, the output is again 0. It is only when the inputs are different, 0 1 or 1 0, and only in these two cases, do we get an output of 1, right? So we'll apply this logic to this particular example. So let us start. Our first bit is the binary value 0. Now this MSB, we will first copy it down directly, and this becomes also the MSB of the gray code. Now from here onwards, the procedure will be like this. We will take each bit of the binary and XOR it with the next bit. So we'll take 0 XOR 1, when we take 0 XOR 1, this we know is 1. Then we'll take 1 XOR with the next bit, which is 0. So 1 XOR with 0 is, this will give us 1. Then again 0 XOR with 1, this will of course give us 1. 1 XOR with 0 is 1. 0 XOR with 1, since the bits are different, this will give us 1. And now observe here, 1 XOR with 1. This XOR operation, when we carry out 1 XOR 1, here is our row from the XOR table. 1 XOR 1, this gives us 0, and 1 XOR with 0 gives us 1, and therefore our result becomes 0 1 0 1 0 1 1 0. This is of binary. This is equivalent to 0 1 1 1 followed by 1 1 0 1. This is of the gray code. This is how we can convert the binary value into its equivalent gray code. So here we have directly used the truth table to do this conversion. Now we have a shortcut. We can of course refer to this truth table, but if we observe, what this truth table is essentially telling us is that when we take two similar values and XOR them together, the output is 0. For example, 1 XOR 1 is 0. But when we XOR two dissimilar values like 0 1 or 1 0, in that case the output becomes 1. And we can use this shortcut now to bring about this conversion. So let us take again in this example 0 1 1 1 0 0 1 0. This is our binary code, and we'll convert it into the gray code. Now we need not even refer to this table, because essentially what this table says is what we'll be making a shortcut here. If adjoining bits are same, we will write a 0, and if adjoining bits are different, we'll write a 1. So let us start. First, the most significant bit of the binary, it is copied. So this is simply copied, and it becomes the most significant bit of the gray code. But now observe this. Compare two bits which are successive, two adjoining or adjacent uh, bits. So 0 1, two bits. If the adjoining bits are same, write 0, and if they are different, write 1. So these two bits are different, so we write 1. Again 1 1, adjoining bits are same, so write a 0. 1 1, adjoining bits are same, write a 0. 1 0, adjoining bits different, so this we put it out as 1. Same adjoining bits, 0. Different adjoining bits, this gives us 1, and this again is different adjoining bits, this gives us 1. So essentially we have used the same truth table, but instead of referring to this every time, we just use a simple logic. If bits are same, adjoining bits are same, write a 0, and if adjoining bits are different, write a 1. And therefore we have the equivalent gray code represented by these bits. Now let us take the example of converting a decimal number to the gray code. Now to convert a decimal number to the gray code, we must follow two steps. The first step is we first convert the given decimal number to its equivalent binary value. So we know this, that this 23, we can convert it into the binary by repeated division by 2. So this is 2, 11 times is 22, that gives us a remainder of 1. Again 2, 5 times is 10, that gives us a remainder of 1. 2 times is 4 with a remainder of 1. 2 1 times is 2, and there is no remainder. And now 2, since the quotient here is less than 2, 0 times will be 0, and that gives us a remainder of 1. And now of course we take these remainders in the reverse order, and we have 23 of decimal is 10111 10111. And now to convert this bit pattern into the equivalent gray code, we again first copy down the most significant bit of the binary, and that becomes the most significant bit of the gray code. Then we compare these two adjoining values. If the values are different, we write this as 1. Again, we compare these two adjoining values. Since these two adjoining values are different, the result here will be 1. Since these two adjoining values are same, we write a 1, we write a 0 here. Since these two adjoining values are same, we write a 0 here. And therefore 23 of decimal can be written as 11100 in the gray code. This is how we convert a decimal number into a gray code. Of course, by first going through the intermediate state of converting it into a binary number. Hi, welcome to this video session on conversion of gray code to its equivalent binary value. Supposing we are given a gray code which is 101101. This is a number. We want to convert this into its equivalent binary value. Now, before we start this, we'll again keep our XOR truth table in front. If A and B are the inputs, and we know that A XOR B, in this case, since both A and B are 0, the output will be 0. A0, B1 XOR value is 1. When A is 1, B is 0, the XOR value is 1. And again, when A and B both are identical, then output is 0. So from this truth table, we can observe that when A and B are same, then the output is 0. And when A and B are different values, the output is 1. Now we'll use this to find the equivalent binary value. So here is the gray code that is given to us. We write the bits 101 101. Now the first step in finding the binary is we will copy down the bit 1, that is the most significant bit of our gray code. So this is the most significant bit of our gray code. We will copy this bit into the most significant bit of the binary value. So this is the MSB of the equivalent binary number, and this bit will be simply copied down. Now from here onwards, how do we calculate these bit values? So we will take each value that we have obtained here. So we will take this value and we'll XOR it with the next bit of the gray code. So 1, we'll XOR it with 0. So that will give us 1. So this is the XOR operation that we are seeing here. 1 XOR 0 is 1. Again, this 1 XOR with 1, that will give us 0, because we saw that when both the bits in an XOR operation are identical, then the output is 0. Again, 0 XOR with 1 will give us 1. This 1 XOR with 0 will give us 1. And here 1 XORed with 1, since both bits are identical, this will give us 0. And therefore we can say that 101101, this is of the gray code. So let us just write this subscript as GC, gray code. This is equivalent to 110110110110. This is of the equivalent binary value. Now in this second example, let us take the conversion of 010101 into its equivalent binary value. So here we have again the gray code, the bits that are given to us 0101 0101. This is our most significant bit. And how do we get this binary value? Let us observe. So the most significant bit of the gray code becomes the most significant bit of the binary. So this value is simply copied into the MSB of the binary. But thereafter 0 XOR 1, we will XOR this 0 with 1, that gives us 1, and then again 1 XORed with 0 gives us 1. This one XORed with one of the gray code, this gives us 0. 0 XORed with 0 is again giving us 0 because both bits are identical. So from our truth table we know when both bits are identical, the output is 0. And here we have 0 XORed with 1, that gives us 1, and therefore we can say that 0 1 0 1 0 1 of the gray code is equivalent to 0 1 1 0 0 1 of the binary. So this is how we convert a gray code into its equivalent binary value. In this third example, let us see how we convert a gray code into the decimal number. Now, this will involve two steps. In step 1, we will first convert the gray code into its equivalent binary value. So, assuming our gray code is the same as we had in the earlier example, 0 1 0 1 0 1. So, we write the gray code bits 0 1 0 1 0 1, and we convert this into its equivalent binary. So as we saw in the previous example, the MSB of the gray code is copied and it becomes the MSB of the binary code. So this bit has been copied. Then after that, we take the newly generated bit of the binary and XOR it with the next bit of the gray code. So 0 XOR with 1 will give us 1. This one XOR with 0 gives us this one. So at every step you can see that the new bit that is produced in the binary, it is XORed with the next bit of the gray code. So 1 XOR 1. 1 XOR 1 is 0. There we have it from our XOR truth table. 1 XOR 1 is 0. So we generate the 0. Again 0 XOR with 0. So again we have from the truth table 0 XOR with 0 is 0, and 0 XOR with 1 gives us 1. So we now know that this gray code is equivalent to 011 001. So this number that we have is the equivalent binary value, and we know now from our previous session that we can convert this into the equivalent decimal value, and that becomes 25. So this is 011 001 of the decimal. We attach a weight to each bit. So this bit has a weight of 1. Since the bit here is 0, its corresponding weight is 2, which is ignored. So let us just write the weights below each. So 1, this will have the weight 2, this will have the weight 4, this has the weight equivalent weight 8, this bit has the equivalent weight 16, and this bit has the equivalent weight 32. Now wherever we have the bit positions as 0, we ignore the weights, and then we are left with 16 plus we have a 1 bit here, so plus 8 and plus 1, so that becomes 25, and therefore we say that this equivalent value is 25, and therefore 0 1 0 1 0 1 of the gray code is equivalent to 25 of decimal. This is how we convert a gray code into its decimal value.